Edexcel A-Level Maths, Year 1, Chapter 5, Pure Maths, Straight Line Graphs. This chapter covers quite a lot of content. Hopefully most of it is familiar from GCSE, but there's all sorts of useful tricks you can use and important key ideas that flow through the entire chapter. We're going to make sure we've reviewed some GCSE knowledge, refresh your memory about things like y equals mx plus c, parallel and perpendicular lines, etc. And then we're going to explore some methods for solving common problems, what kinds of skills you'll need to be able to demonstrate. We're even going to look ahead a little bit at how these skills are going to become useful when you're looking at more complex problems, especially in terms of dealing with circles. So to start with, I'd like to have a little think about the statement, all straight lines can be described by the equation y equals mx plus c. Have a think about it and decide whether you agree or disagree. A good way to think through something like this, when I make a sweeping statement about all straight lines, see if you can prove me wrong. Try to be that annoying person who finds the edge case or the exception to the rule. Can you think of a valid straight line that you could draw on a two-dimensional grid that can't be described by an equation like that? So where do we go? Well, let's think about it for a start. A few pointers to get you going. Hopefully we recognize that when a line is written in this form, we can extract information from it. Although there are 4 letters in that equation, 2 of them are variables. Y is the output variable that you plot vertically, and X is the input variable that you'd be plotting horizontally. But M and C are normally numbers. In this case, we've got placeholders. M and C represent constants that we don't yet have values for, so we can describe a whole family of different straight lines. But often you might have actual numbers in there. Y equals 3x plus 7. Y equals minus x is just a gradient of minus 1 and a y-intercept of 0, and so on. So if we've got m as the gradient and c as the y-intercept, in other words, the height at which the line crosses the y-axis, then as long as all straight lines have a gradient and a y-intercept, they can all be written like this. We just plug in those numbers for the gradient and the intercept. But I wonder if you've considered some of these slightly strange edge cases. Y equals 0. Can we come up with a gradient and a y-intercept for that one? Does it still work? Are there any numbers you could use for m and c that would make that equation valid? What about x equals 3? If we get really creative, x equals y equals z. I suppose that last one, this is the reason I try to restrict our thinking to 2 dimensions, because if we start to extend, as you might do later in the course, to looking into the 3rd dimension, then there are perfectly valid ways of creating straight lines that pass through 3-dimensional space. If you can visualize the coordinates 0, 0, 0 and 1, 1, 1 and 5, 5, 5, so you go to the right 5, in 5 and up 5 or something like that, then you've basically described a few points on the line x equals y equals z. But to save us complication and worrying about the 3D things, we're going to focus our attention just on the 2-dimensional plane. And we're certainly not going to mess around with things like this. This one wouldn't even be a straight line. Z equals 3 is a bit like describing a vertical height of 3 in 3-dimensional space, which is what we call a plane. So basically an infinite flat surface that's parallel to the xy axis, or parallel to the xy grid, but 3 places higher up. We'll leave those 2 questions at the bottom. If you do further maths, you'll explore more about it. But the 2 at the top, what about y equals 0 and what about x equals 3? These are worth exploring a little bit further. So y equals 0 looks like it might be a counterexample, but actually, as long as we're careful, we can make this work for us. If we set the gradient to be 0, then we have y equals nothing times x, which is perfectly fine. And if we set the y-intercept to be 0 as well, then we have y equals nothing times x, add nothing. Y equals 0, add 0 is y equals 0. So it's not a contradiction, it's just a very trivial example of this line. Gradient 0, that makes sense, it's a flat horizontal line. It doesn't slope up or down, so it has a gradient 0. And a y-intercept of 0, well, the y-coordinate is always 0, so at the point where it crosses the y-axis, it also has a y coordinate of 0. More interestingly is this one, x equals 3. Y doesn't appear in this equation, and that's the crucial bit. To create an equation of the form y equals mx plus c, you have to have a y at the beginning. If there isn't a y at the beginning, we can't create our equation. And if you want to visualize a line like x equals 3 and ask the question, well, where is the y-intercept, or what is the gradient? Both of those become problematic questions. X equals 3 is a vertical line. So you can't say move along one space and see how many spaces you go up, because as soon as you move along one space, you've lost the line. The line is vertical. It doesn't move along. It moves straight up and down. And similarly, it's not going to cross the y-axis. X equals 3 is parallel to the y-axis, so it has no y-intercept. You can't say it's 0 because that's actually a location on the y-axis. It doesn't have a y-intercept. If you make it x equals 0, then it has the opposite problem. It crosses the y-intercept everywhere on the y-axis. It has a y-intercept everywhere because it is lying on the y-axis, which is also problematic. You can't find a single value for c because there isn't one. So, in general, it is still a useful format, apart from these little edge cases of x equals a constant, which you can easily deal with separately if you need to. The vast majority of the time, you absolutely can use y equals mx plus c to describe your lines. Pretty much every line you draw is going to be a line that has some kind of slant to it. It's either going to be sloping upwards or sloping downwards a little bit, and therefore you can figure out where it crosses the x-axis and where it crosses the y-axis. But if you're dealing with a perfectly horizontal line, it won't cross the x-axis at all unless it crosses it everywhere. And similarly, with a perfectly vertical line, it won't cross the y-axis anywhere unless it crosses it everywhere. However, if we want to avoid even those minor niggling points that cause some contradiction, we can describe all possible straight lines with this slightly more generalized form. The small disadvantage here is that this format doesn't easily lend itself to extracting information about the gradient or the y-intercept. I know we've still got a c in this one, but it's not the same c as the one above. So if you assume that if it says 3x add 4y equals 5, it must cross the y-axis at 5, that's not quite how it works. But you can rearrange between the two formats. So if you've got one that looks like this, you can rearrange to the other one fairly easily. Now, another thing you might not have considered when it comes to straight line equations is how easily you can draw the graph of the straight line. It can be quite nice for people to always be looking at straight line equations in the form y equals something times x add something, because they can start on the y-axis at the point 0c, and then they can move along and up according to how big m is, maybe along and down if m is negative. But ax plus by equals c is actually not too difficult to sketch, because to find out where a line crosses the y-axis, all you need to do is set x equal to 0. The y-axis is equivalent to the line x equals 0 after all, so solve them simultaneously. It's the same as making x equal to 0 in your equation. If x is 0, then the ax bit disappears, and you get b times y equals c. So y is c divided by b. You can do exactly the same thing to find out where it crosses the x-axis. Make y equal to 0, and you get a times x equals c, so x equals c divided by a. So with two very quick calculations, you've got a point on the x-axis, a point on the y-axis, join them up and you've got your straight line. This is probably the most important part. This is the main task you're going to be working on during this video. We have a series of skills that you're going to be developing as you work through the chapter, and each skill has got an example question so you can get a feel for exactly what's going on. You might want to skim through, take 5 or 10 minutes before you properly dig into this and identify any of these skills that you think, yes, I remember how to do that. That's a skill that I'm familiar with. I'm confident I could do any question that involved this. I'm going to give it a smiley face or a tick. And if you see a skill that you think, I don't even know how I would begin something like this, give it a sad face, give it a cross, color it in red, whatever's going to be helpful for you. Then you can focus your attention mostly on the areas and the skills that you've either forgotten or never quite made sense to you in the first place. To go along with this, you might find it helpful to have your textbook handy. Exercises A, B, C, D, E, and F all have different focus points for you. So if you're looking at gradients, or you want to find out how to determine where two lines cross, or you want to create a line equation either from points that it goes through or from other clues like it's perpendicular to this, etc. There are exercises that are relevant to all of those. But I think the skills that I've listed here, I've got 12 skills and 12 corresponding example questions. They will give you a good cross-section of pretty much everything in the whole chapter. So if it feels a bit daunting, don't worry. It's an entire chapter's worth of work. There'll be more practice you can get on this, but this is going to be a really useful starting point for you. I'd encourage you at this point to pause the video, to work your way through this list, identifying the areas that you are confident with and highlighting the areas that you're less sure about. You might want to have a look at the textbook and flick through so you see a wider range of example questions. If you look at the mixed exercise at the end as well, that's a good way to see a range of different questions in a different context. So it's not obvious that they're all talking about the same skill. It'll be a mixture of different straight line skills involved. And I have one other thing to suggest before you pause and go away to have a think about things. And that is the crucial overlap between algebraic reasoning, where we're working with equations and numbers, and geometric reasoning, where we're thinking more in terms of shapes, lines, angles, and all of that sort of thing. Because graphs and sketching graphs requires both of those two things. And it's one of the most important and also one of the most challenging areas for a lot of students doing A-level maths. But it can make such a big difference to your level of confidence with these problems. So let's get into the important question. If you've got a formula, if you've got a rule that you know should work, why would you bother with a diagram? Can't you just do it with the rule? Well, yes, you could. But here's a couple of things that the diagram will do for you. First of all, it'll give you a fresh perspective. It is basically a way of seeing the entire set of possible output values for different input values all in one go. It'll allow you to see things about a problem that wouldn't be immediately obvious if you were just working with equations. Yes, if you've been given a couple of points and asked to find the gradient between them, there is a mathematical numerical approach for that. There's a formula if you really want to memorize a formula and plug numbers into it. But it's easy to make mistakes with a formula. And it's not obvious when you look back at a small calculation you've done, 3 take away -4, etc., etc. It's not going to be obvious if you've dropped a minus sign, or if you've got two numbers written the wrong way round, 4/3 instead of 3/4. Whereas if you have a diagram drawn and you're trying to calculate the gradient between 2 points, you can immediately get a sense check that your diagram and your algebraic solution match up with each other. So the first part here is that it helps you solve problems, because you'll see how to approach a problem in a way that wouldn't be immediately obvious without it. It's especially useful if the problem feels a bit unfamiliar, if you're trying to find the area of a triangle, or you're trying to work out the distance between a line and a point. And the next part is verification. If you try to calculate the gradient of a line and it comes out as a positive number, and then you look at your diagram and it's clearly going downwards as you move to the right, you know you've made a mistake somewhere. So you can either double check where you've put your points, or you can go back to your equation and see if you've made a sign error somewhere or other. Okay, go have a play with these, and then when you're done, come back to the video, unpause, and I'm going to break down each separate section and show you not a complete solution for any of the questions, in fact, but I am going to show you what the value of a diagram would be for each of these, and talk a little bit about the kind of approaches you can take. Welcome back. Hopefully you've had a chance to get stuck into some of these. Hopefully there's a few of them that you were able to calculate already and you're confident with, and there'll be some others where you're a little bit rusty. Now I'd encourage you, even if you know what you're doing with some of these early ones, to not skip ahead too soon, because I might be able to tell you something you've not thought about that makes your method go from being perfectly usable to being more efficient or quicker or less error prone. For the very first one, find the gradient of a line from a parallel line. Well, essentially what we're looking at here is, here's a line that we know, so I've drawn that in black, and then line L1 is a line that we don't know. We're not told exactly what line L1 is. We're just told that we want to find the gradient of it. And the important step here is to recognize that we don't actually care what the equation of this new line is. All we care about is what the slope of the new line is. And since they're parallel, the slope of the new line is the same as the slope of the original line. So the question has boiled down to, can we find the gradient of the line that we were given, 3x add 2y equals 4. And after all my fancy talk about how ax add by equals c might be a more useful format in general, it's not the easiest one to read off a gradient from. So my first step here would probably be to rearrange the equation so I can identify what's the number in front of x when the equation is written in the correct format. If it says y equals something x plus something, then I can read off the gradient. For the next one, it's a very similar idea. We're just looking for perpendicular lines instead of parallel lines. And there is a rule that connects parallel and perpendicular lines, but I like a visual for this as well because it helps me to see why the rule makes sense. If the original line, like this one, has a steep negative gradient, I'm expecting the perpendicular line to have a shallow positive gradient. Steep becomes shallow, and alternatively shallow would become steep, and negative becomes positive, and alternatively positive would become negative. So the change in the steepness comes through a reciprocal process. If you've got a gradient of 5, the perpendicular gradient should have a size of a fifth, shallow going with steep. But in addition to making it the reciprocal, we also change the direction. So positive gradients become negative, negative, positive. You can see this for yourself if you've got anything perpendicular around. So grab a bit of paper, you can turn it at any angle you like, and the gradient of the longest side of the bit of paper is always going to be positive when the gradient of the shortest side is negative, and vice versa. The only time that kind of breaks is when one of them is perfectly vertical and it has an undefined gradient, because you could think of it as either positive infinity or negative infinity, and the other one will be perfectly horizontal with a gradient of 0. And the reason it breaks there is because you can't divide by 0. There is no sensible reciprocal to the number 0. Okay, and the last one, a little less annoying for the eyes perhaps. This one is a static image. We've got 2 points that we're given and we're asked to find the gradient between the points. So there's a line that's defined by these 2 points. 2 points is always enough to define a line. If you give me 2 different points that lie on your line, I will know for sure where your line is. I just join up those points and continue in the same direction either way. It's worth noticing we weren't asked to find the equation of this line. I think that comes later in your list. We're just asked for the gradient. So it's all about the slope. But notice how when I've got a picture, it makes it a lot easier to visualize what kind of answer I'm expecting. So it should be a negative gradient, for instance. And also it's going to be easier to identify a method. If the gradient is how far you go up compared to how far you've gone along, I just need to measure the vertical offset and the horizontal offset and divide vertical by horizontal. And also if I haven't gone up, if I've actually gone down as I move to the right, then I'll treat that as a negative. Chances are you could make something quite nice out of this just by filling in a couple of extra lines. Then we've got a nice visual for how far you've gone along and how far you've gone up or down. If you can calculate those numbers, that gives you your gradient. Next few points. Find an equation from a y-intercept and a gradient. So for this one, you probably honestly don't need the equation turned into a graph for you. But if you were curious about what the curve or what the graph of this straight line should look like, it's going to be something a little bit like this. I quite like this visual for gradient. If you think of a gradient as being the slope, and you think of the slope as being the ratio between vertical and horizontal distance, sometimes called y step divided by x step, or just rise over run, is a nice quick way to say it, then you can easily visualize a gradient of 3 because it just means the line has gone up 3 for every 1 you go along. Now the key bit for actually creating the equation for this one is to understand that y equals mx plus c gives you the equation of a line with a gradient m and a y-intercept of c. Now that should be a bit easier to do than some slightly messier ones. So this next one talks about the equation of a line through the point -1, 5 with a gradient of -2. And in this case, I think the diagram does give you a nice extra way in. It lets you see that if your gradient is -2, you can move along 1 and down 2. Well, that would literally take you from the point -1, 5 to the point 0, 3. And suddenly you've found the y-intercept. Now you've got the y-intercept, you can go back and use method 1, y equals mx plus c, use your known gradient and your known y-intercept. Now there is a slightly more sophisticated formula that you can use to create the equation of a line from any known point and a known gradient, and that's going to be the most efficient way to construct your answers to questions like this in the future. But we'll get to that. We'll cover those details when we reach that part of the chapter, or you can look ahead if you're curious. You're looking for a formula that looks something like y minus y1 equals m brackets x minus x1. And it's a nice way to basically take a standard straight line and translate it, move it, shift it so that it goes through a different point, and then we don't have to rely on knowing where it crosses the y-axis in order to find its equation, and it makes life a lot quicker for us. Now the last one is where they've not given you the gradient at all. All they've given you is the 2 points. You might recognize those 2 points from the earlier questions, so you get to reuse some of your diagrams. If we need the equation of this line, there are 2 elements to that. We need the gradient, which you might have calculated previously, and you need the y-intercept. That's the best way to create the equation of a line from something like this. Alternatively, the gradient and a single point would be sufficient. So if it's obvious what the y-intercept is, like in this case, it seems to pass through 0, 6, and we can double check that it is exactly 6, not 6.1 or something awkward like that, then you can use y equals mx plus c as soon as you've got a gradient. If not, well, we can use our special formula for the equation of a straight line that you'll study in more detail at a later date. The next section is to do with line segments. Now technically, when you have a line, we define it mathematically as going on forever in both directions. So there's no limit, there's no upper limit, there's no lower limit, it just continues forever. We draw a distinction between that and something like a ray. A ray line, or sometimes known as a half line, has a well-defined starting point, and then it just goes in one particular direction. So imagine marking the point 3, 4, and then drawing a horizontal line moving to the right, but not moving to the left from that point. That would be a half line. Well, this is the next level on from that. We have a starting point and a stopping point. So it's not a line exactly, it's known as a line segment or a piece of a line. And because it has a finite starting and ending point, it also has other properties that we associate with, lengths in shapes and so on. It's got a length, it's got a distance. We can calculate the length, and we can calculate things like the midpoint between 2 lines. I like the visual for this one because there's lots that you've learned how to do with shapes, with geometry, and now we're just being given a question that involves numbers, coordinates, x's and y's. Maybe you've been given an equation, maybe you're being asked for an equation, but it doesn't immediately jump out as a triangle problem. And yet, as soon as you draw the triangle, you can start to see that it is. I'm looking for the distance between A and B, but the distances that are most readily calculable from this are the horizontal and vertical offsets between A and B. I can work out how far I need to go sideways, and I can work out how far I need to go up. And then suddenly you're dealing with a classic right angled triangle problem. So if you know how to do Pythagoras, then you can turn 2 shorter distances into the length of the hypotenuse, the longest distance. There's another nice thing about your midpoint, which you can see from this same diagram. If you scan down and across, you might recognize that the midpoint is not just halfway along the diagonal line, it's also halfway sideways between A and B, and it's halfway vertically between A and B, which means there's a really quick, lazy way to find the coordinates of the midpoint. You just need the average of the x coordinates, and out pops the x coordinate of your midpoint. You take the average of the y coordinates, and that gives you the y coordinate of your midpoint. The halfway point between any 2 numbers you can always find by adding the 2 numbers and dividing by 2. That's particularly convenient when your numbers are quite far apart, or they're awkward fractions, or there's a negative involved. It's all very well saying what's halfway between 8 and 12. We can all do that one in our heads. But if I said what's halfway between 8 and 27, you're going to spend a long time counting up from 8 and counting down from 27 and hoping you've not miscounted. It's a lot easier to do 8 add 27. So what's that? 35, and then divide by 2. 17.5. That is the midpoint between 8 and whatever number I said before, 27. In this case, similar thing. -4 and 2 have a midpoint of -1 because 2 add -4 is -2. divide by 2 and you've got -1. The average, the midpoint of the x coordinates and the midpoint of the y coordinates gives you the midpoint. In terms of the equation of the perpendicular bisector, that's a useful one because it combines a few previous skills. So I don't want to give too much away in terms of this one, but we've already talked about how we can find the midpoint, and half of what a perpendicular bisector is a bisector. It cuts the thing in half. And then the perpendicular section of it is suggesting that what we need to be doing here is finding a line that is at right angles to the line we've already got. So imagine drawing a line through that midpoint that is at right angles to the line we already have. If we've got tools for calculating perpendicular gradients, and we've got a tool for going from a gradient and a point to the line equation, then we're sorted. These next three involve triangles. If you don't sketch the points out on a graph, it's going to be much harder to identify a nice efficient method for this, because these sort of ramp up in difficulty. The very first one, as soon as you see the diagram, things are going to feel a bit easier. The second one, a bit more work, but if you do enough work, if you're careful with your diagram, and if you can calculate some gradients, you might recognize there's a method that you could use that maybe you wouldn't have thought of before. The third one is the most awkward, because the points could literally be any 3 points, and you can test this out for yourself as well. If you get GeoGebra and just mark 3 random points to create a polygon, it'll tell you the area. Then you can see if you can calculate the same number for yourself. So here's our first one. Hopefully when you see that and you think about the triangle it describes, rules for area of triangles jump into your head and you start thinking about what the base could be, what the perpendicular height could be, where those numbers are going to come out the most easily. And it shouldn't be too difficult a problem to solve. But I hope you can appreciate why the diagram makes it feel quite different to just here's 3 points, help, I don't know the formula. You know how to find the area of a triangle like this. It's a right angle triangle where we have enough information to find all the distances if we need. So that's more than enough to find the area. This next one, if you look carefully at it, you might notice it looks like it might also be a right angle triangle. Now, using that fact is not essential for finding the area. There are lots and lots of ways to find the area of this. So I don't want to jump in and say here's the method, because there are lots of them. And in fact, I'd encourage you to pause and have a play around with this before you get too far in, because I want you to come up with a few different ways to find these areas and then decide which one you like the best and figure out if some of them would be more suitable for certain situations than others. I've said here find the area of a triangle from 3 line segments, 2 of which are perpendicular, because that sometimes gives you a shortcut. Although it looks different to the first example, if it's still a right angle triangle, there's no reason why you couldn't still use your right angle triangle techniques. The only slight catch is it's not as straightforward to find the length of those 2 perpendicular sides. But then that just reduces to a problem that we solved previously. Each diagonal line you want to find the length of, you can do that by using right angle triangles. You just got to create the appropriate right angle triangle, and then you'll be able to see how to use Pythagoras to calculate the diagonal length. This last one is the messiest of all. You might think that AC and AB are perpendicular. You could do a quick check. You could find the gradient of each of them. And if they really are negative reciprocals, if one is both the negative and the reciprocal of the other one, then you would know they are perpendicular. But if they're not perpendicular, we can't use them as if they were the base and the height of the triangle, because they're not. Anytime you mess with that right angle, you change the behavior of the triangle. You make the area smaller than it would have been if it had been a right angle. But once again, there are tricks that we can pull for something like this to make our lives easier. If you've had to think about this and you've come up with some ideas, you might have realized that it is possible to calculate the length of all 3 sides. And then your problem has been reduced to a trigonometry problem. If I have a non-right angle triangle where I know the length of all 3 sides, is it possible to find the area? Well, there are some formulae that will do exactly that. There's something called Heron's formula, spelt like the bird, H-E-R-O-N, if you want to look it up. It's not on the A-level specification. It's not something you'll be routinely asked about. But if you have a triangle with 3 known sides, it is possible to calculate the area without doing any sine, cos, tan, trigonometry type stuff. But most people with a situation like this, known three sides, would probably use cosine rule to find one of the angles. And once you've got an angle, there is a formula using the sine function, half AB sine C, that gives you the area of a triangle. But I'm going to show you one slightly nicer method. I don't want to throw away right angle triangles just because I can't see any on the screen. With the previous diagram, I was actually able to make some. If I carry on, make another one, you might start recognizing that what I've got here is pretty much a rectangle made from three right angled triangles and then one triangle in the middle, which also happens to be right angled in that case, but there's no reason it would have to be if I use the other three triangles to do my calculations. Look at this. If I make a rectangle around this triangle, sometimes called a bounding box, because we define its highest and lowest and leftmost and rightmost points by working out the maximum, the upper and lower bounds of where the triangle can go. Once we've got this box, what you're looking at is a rectangle, which is easy to find the area of, and three right angled triangles. Not only are they right angled, but they're oriented more like this one. They've all got nice horizontal and vertical sides. And that method, a variant on this, is how a computer will calculate the area of a random polygon in two-dimensional space on a screen. It's going to break it into triangles. For each triangle, it will basically do something like this. Well, that's one of the possible methods that can be used. And it's really quite elegant. You don't need to know anything about sine, cos, or tan. Suddenly you can solve the problem without a calculator, because it all boils down to nice right-angled triangles. So if you found a method like that, very well done. If you went through the longer method and used cosine rule and the sine formula, also well done. If you've come up with another method that also works, brilliant. When you do vectors in year 2, you might have some more methods that might be even more efficient for you to use. So watch this space. This final section is a bonus section. So depending on whether you've already done enough work, you might want to pause here and give up on this, come back to it another time. But there are a few questions on straight lines that are quite popular with entrance exams like the MAT, the Mathematical Aptitude Test for Oxford, and Imperial and Warwick and various other places. And you'll find that they feel a little bit different to some of the questions that you're used to getting used to. They're not necessarily going to be regular standard A-level maths techniques. So I thought it might be worth having a little look and talking a bit about how our graphical approach can help you with this as well. So the first question here that I'm going to look at, I'm going to skip question 1. That's from a STEP paper. That's the 6th term examination paper for Cambridge. Those questions tend to be a bit more involved, and some of those questions are designed to take you 30-40 minutes. We're going to look at some of the short form questions from the MAT paper because we haven't got 30 or 40 minutes to spend right now. But let's start with question 2, the reflection of a point in a line. The very first thing I would do here is draw a sketch. I can create the line equation and create the straight line graph by asking the question, when does the line cross the x-axis, when does it cross the y-axis? So if x is 0, 4y equals 50, so I can find the y-intercept, 12.5. If y is 0, then 3x equals 50, and the x-intercept, or the root, would be x equals 50 over 3, so about 16 and a bit. So once I've sketched it, I have a rough idea of where it is and what it looks like, and I've got the point 34 marked on there for good measure. I've also faintly marked on where I think the reflection of that point would be, and this is going to help me to start making sense of the problem. The crucial thing to know about reflections is that if you draw a line between an object and its reflection, that line will go straight through the mirror line or the reflecting surface at right angles. So it's like a shortest distance problem. What's the most efficient way to get from that blue cross to the dotted line? Well, it's not going to be to travel this way or even this way. It's not going to be to go all the way up to there. If you want to get to the line as quickly as possible, you're going to go as directly as you possibly can. You're going to want to travel perpendicular to the line. I'm not drawing that very clearly, but you get the idea, hopefully. If you go perpendicular to the line, then that is automatically the shortest possible distance. And it turns out your reflection is the same. If you can find a line that is perpendicular to the line you're on, then you've automatically found the line that reflections go through. And that's the trick with this. It's about identifying what the problem is asking you in terms of skills you already have. So if you know how to find perpendicular lines using the gradient of the line you're given, if you know how to find the equation of that line, and then if you can work out distances, then you've got most of the tools you need for this. It might be helpful, I have to say, with this particular question to find out where your perpendicular line crosses the line you were given. So solve the two line equations simultaneously and you get an intersection point. Here's the next one, and this one is a shortest distance question, so it is very closely related to the reflection one. The shortest distance from the origin, in other words the point 0, 0, to the line that's given, 3x add 4y equals 25, is what? You just got to figure it out. I quite like this question because it's got a few different ways that you can approach it. The standard approach is a perfectly valid one for students to apply. It's a good one to roll your sleeves up and get stuck into. The key information you need, once again, is that the shortest distance is always perpendicular to the line. If you try going any other distance, what you'll end up doing is creating for yourself a right-angled triangle. So if I go, let's say, to if I try traveling from the origin to this point, assuming that that other point on the line is closer, what I've drawn is the hypotenuse of a right-angled triangle. And because the hypotenuse is always the longest side of a right-angled triangle, it's always going to be longer than the red arrow that I've drawn. So that basically proves that the closest distance, the closest approach, the shortest distance is always going to be perpendicular to the line. Once you know that, you can find the gradient of your line, use that to find the gradient of the perpendicular, use that to find an equation of a line that passes through the origin, maybe solve that simultaneously with the original line, find the coordinates to the point where they cross, and then finally use Pythagoras to get the distance between them. I did say there was going to be some more efficient tricks for this, and the hint I'm going to give you is to look for similar triangles. So think carefully about the ratio of the side lengths, and that might give you a clue as to what's going on. The other thing that's really elegant and pretty here that you can play with is the areas of the triangles that you've made. Because I say triangles plural, there's the one big obvious triangle that's formed by the x-axis, the y-axis and the dotted line. But there's also the little triangles that you've split your bigger triangle into. They're both right-angled triangles that have the same ratios, but we can find the area of those. And if you can find the area of each of them separately, you can use that as a sort of backdoor approach to finding the length of the red arrow. And last, but by no means least, this is quite a nice visual of what happens when you reflect a point in a line that can change. Now, when you see a question that has y equals mx rather than y equals 3x or y equals 7x, it's tempting to think, well, I can't draw this diagram because the diagram is always going to change. If you've got GeoGebra or Desmos and you can put a slider in like I've done, sure, you can draw a whole bunch of lines that somehow represent that entire family. But how do you do that if it's just you in an exam or scribbling on the back of a bit of paper to try to do your MAT question? Well, the answer is you don't. You don't try to draw all of them. You draw one or two representative lines. Don't make them too simple. Don't go with y equals 0x. Don't go with y equals x. Try to go with something a bit less trivial like y equals a half x or y equals minus 2x or something, so that it's different enough that you can do some thinking about what's going to happen. Now, if this gradient becomes negative, then the point is going to go to a different place. And if the gradient is exactly 1, then the point 1, 0 gets mapped to the point 0, 1. So there's a couple of things that you can use as a sort of sense check. If I've done this right, then this point should go to over here. But in terms of making sense of exactly where the point is going to go, I'd recommend drawing on a few little lines. So make yourself some vectors that describe how far along and how far up you've gone, and use the fact that the reflection will always be perpendicular through that point. Another thing you can do here, if you've made sense of the first question on reflections, is do the same things, but this time you don't have a number to work with. you have a letter, you've got M. So try it algebraically and see how far that takes you.